Okay, hey there. So we're going to do some notes today on simplifying radicals and some stuff with um, rational and irrational expressions. Okay, so before we get into it, I do want to go ahead and do a warm up. So go ahead, pause the video, and try the do now. So you have three questions. You're just messing around with your calculator and you're seeing if you can get each one to work. So pause the video for a moment and see if you can do these. Okay, so let's see. We needed to find a number that we can multiply by itself to get 144. If you got 12 times 12, good job. Another way we can write 12 times 12, of course, is 12 squared, or 12 with a little exponent 2. Okay. A number you can multiply by itself 3 times to get 125. This might have been a little more challenging, but if you got 5 times 5 times 5, or 5 cubed, that would have worked. And just to practice plugging it in the calculator, right? 5. Now we could use the little caret button up here to raise it to the third power. Or we could do 5 times 5 times 5, right? A number you can multiply by itself 4 times to get 256. Well, coincidentally, that number itself is 4. 4 times 4 times 4 times 4, or 4 to the 4th power, right? Another way we could even write it would be 4 times 4 is 16. 16 squared. It's always nice to make those connections. Okay. So I'd like to recall, we talked about rational and irrational numbers a couple weeks ago. And I want to kind of recall those definitions. So, we said that rational numbers were numbers that could be written as some fraction a over b. And I want to clarify there that a and b, they both have to be integers, right? And when we talked about the integers, we said those were the positive and negative whole numbers, right? So a and b have to be integers. Okay, rational numbers include all fractions, so anything we can write as a fraction, all decimals that end, and repeating decimals. So, 1/4, 0.57. Repeating decimals, 3.666, etc., or 3.6 repeating. Those are all rational. Remember, we can write whole numbers like the number 5. That's rational as well because we can write it as 5 over 1. Okay. The more challenging type of numbers to work with were the irrational numbers, right? Those were the ones that they never end, they never repeat, their decimals go on forever, and we can't really do much with them. So, the one that always comes to mind that everyone likes to talk about is pi, right? Or this would go on forever, but let's see, 3.14159 something, something, something. Okay, a number that you as Algebra 1 students haven't really dealt with, but you will plenty later on in your math career, is the number e. Not the letter E, the number E. We use this E to represent a really cool number that, in my opinion, is more interesting than pi, but not as famous as pi. But it's an irrational number, an infinite number of digits, just like pi. Let's see how many I can get. And that's about as many as I can get. But it goes on forever as well. The thing that we didn't really touch on previously was the fact that the square root of any number that's not a perfect square is going to be irrational. Okay, so something like root 2, which, what is root 2 as a decimal? Let's see. Second square root 2. 1.41421 blah, blah, blah. So this is a decimal that goes on forever, never repeats, never ends, right? It's also irrational. Some fun facts about irrational numbers. Historical fact is, there was a cult, a bunch of old Greek dudes back in like 400 BC called the Pythagorean Brotherhood. You've probably heard of that guy Pythagoras, right? He did stuff with triangles. Well, the Pythagorean Brotherhood, they were a cult, a bunch of wacky dudes with wacky beliefs. One of the things they believed was that when you fart, some of your soul escapes out of your butt. And that kind of conflicted with the fact that they were also vegetarians. So I'm assuming that they consumed a lot of beans and legumes, and they were pretty gassy bros. But the Pythagorean Brotherhood, they thought all numbers were rational. They didn't know that irrational numbers existed. And one of the numbers that they worshipped, I don't know if they worshipped it, but they thought it was magical, was the square root of 2, which is what they get when they applied the Pythagorean theorem to a right triangle with side lengths of 1. They thought this root 2 was rational, like all the other numbers. Well, it turned out it's not. One of their members proved that root 2 was irrational. He proved that it couldn't be written as a fraction of 2 integers. That proof is a little bit beyond our scope right now, but maybe we'll look at it later. So he proved it was irrational, and instead of celebrating, what they did was they took him out in a boat. They said, hey, let's go fishing. They took him out in a boat, and they chucked him overboard. And they drowned him. Poor guy. So, turns out irrational numbers, a little dangerous. Okay, let's talk about how we structure these roots. We need to talk about some vocab when it comes to roots. Okay, so when I write anything in any sort of root, whether it's a square root, cube root, fourth root, etc., there's 3 terms that I have to keep in mind here: the radicand, the index, and the radical. So the radicand, that's my whatever I'm trying to take a root of. Whatever I'm trying to take the root of, whether it's the square root, the cube root, or whatever. The index, that's the number that I put in the little square root symbol or radical symbol. That tells me what type of root I'm taking. So when the index is a 3, that means I'm taking a cube root. Okay, so the index tells us what kind of root, what type of root we're taking. Okay, if we think about square roots, when we take square roots, we never write a little 2 here, but when we take square roots, the index is 2. We just use square roots so often that we skip writing the index for it. But something like this little 3, means I'm looking for the cube root of 3. Okay? So I want to know, what do I cube to get 125? Right? Oh, we cube 5. Okay? The radical, that's the symbol itself. Okay, so that's the entire symbol. Okay, the entire symbol we call the radical. The radicand is what's under the symbol. All right, so let's look at some rationals, and let's see if we can prove, or state at least, which ones are rational and which ones are irrational. So remember, if you can't write the square root as a perfect square, if it doesn't come out perfectly, it's going to be irrational. Okay? If it doesn't come out perfect, it's going to be irrational. So the ways that we can check are we can pop them in the calculator. We can see if it comes out to a nice whole number, or if it comes out to some gross repeating decimal or gross non-repeating decimal. So let's see. Second square root of 40. I don't think I can write that as a fraction. Let's try math frac. Nope. So that's irrational. Let's try the square root of 150. Another gross decimal. Let's convert it to a fraction. Well, this says I can convert it to a fraction, but that might just be some round off error that's occurring. Okay? That might be some round off error that's occurring. So I'm going to go ahead and say that that's irrational because the only reason this is converting itself to a fraction is due to round off error in the calculator. Okay? Let's try another one. Let's see. Well, we know that 36 is a perfect square. So if I make the square root of 36 negative, it's just going to give me a negative number. So where are we at so far? Let's see. So we know this is irrational. We know this is irrational. This just equals negative 6, which is rational. Okay, if we type the square root of 400 in a calculator, we'll get 20, which is rational. Something I'd like you to try is try taking the square root of negative 6. See what you get. Let's see if that'll work. I'm going to take the square root, of not negative 6, negative 36. Square root of negative 36. What does that come out to? Whoa, I got an error. It says non-real answer. Non-real answer. Does that mean there are numbers that are not real? That when you square them, they're negative? Yes. Fortunately, we're not going to worry about them right now, or probably for most of Algebra 1. Okay. I got a few more that I want us to take a look at. So let's see. I want to know if these are rational or irrational. Okay. So the sum or difference of two rational numbers. So I take two rational numbers, a over b plus c over d. Okay. Is that always going to be a result that's rational? And the answer is yes. It's always going to be rational. Okay. What if I add a rational and an irrational number, pi plus 2? Well, the result is going to be irrational. Okay, I won't be able to write this as a fraction because I couldn't write pi as a fraction to begin with. The sum or difference of two irrational numbers. Now, this is an interesting case because if the irrational numbers are different, usually my result will be irrational. However, I could end up with a rational number if these two things add or subtract to 0. You know, if I had pi minus pi, that comes out to 0, and that's a rational number, so that wouldn't really work. Okay. The product of two rational numbers, if I take, one fraction, a over b, times c over d, well, that's always going to be rational. Okay. What if I multiply a rational times an irrational? So, I don't know, pi times 4, 4 pi. Well, fortunately for us, because we can't write pi as a fraction, this answer will always be irrational. Okay. What about the product or quotient of two irrational numbers? Well, pi times e, those are two irrational numbers. Do they multiply to irrational? I think they do. However, what if we had pi divided by itself? One irrational divided by another. Well, that comes out to 1. That's a rational number. So similar to number 7, going to be irrational unless, um, unless the product or quotient is 1 or some other rational number. So how about we just say, it could be either. It really depends. This is a hard question. So it could be either. Could be either. Really depends. Okay. And I think we'll stop there. Tomorrow we'll go ahead and we'll look at some more practice problems, and we'll talk about simplifying radicals as well. But we'll go ahead and we'll stop it there.